So I want to go over an elementary discussion of Pythagorean triples. I'll address a joke that I saw on Twitter. So here's the famous one, the 3, 4, 5. We're going to focus on the ones that don't have common factors. If you have a Pythagorean triple, you can multiply every number in the triple by the same constant and get another triple, right? So for example, I can double this and double that and double that. And when we do that, we get another Pythagorean triple, but it's somehow less interesting. So we're going to focus on the Pythagorean triples that don't have common factors. Those are called primitive Pythagorean triples. And let's say you're in high school or even middle school, and you want to find your own Pythagorean triples, and you want a lot of them, and you know that the interesting ones are the primitive ones, so you're really looking for the primitive ones. So how do you find them? Well, the first thing we're going to do is rewrite this equation. So instead of having a squared plus b squared equals c squared, we're going to have a difference of squares on the right-hand side. Instead of 3 squared plus 4 squared equals 5 squared, we have this. And one reason for doing this is because when we look at this particular triple, 3 squared plus 4 squared equals 5 squared, we notice that we're really interested in the difference of squares of consecutive numbers. That's something that we might be able to analyze easily. So let's try that. Okay, so now we're just looking for the case where c is just 1 bigger than b, right? So 5 is just 1 bigger than 4. So let's try others like that. If we look for 6 squared subtract 5 squared, we get 11 instead of 9. And if we try 7 squared subtract 6 squared, we get 13. And already we're noticing a pattern. So now let's see what we can do with this pattern. Does it generalize? Why is it true? And so on. Okay, we want the difference between 7 squared and 6 squared. So I've just written it out a little bit differently. I want the difference there. And there's no common factor between the 7 times 7 and 6 times 6, so maybe we can go halfway and introduce a common factor. Okay, so instead of going all the way from 7 times 7 to 6 times 6, we'll go from here to there first. I guess that's not exactly halfway, but at least when we break it up into 2 stages, we can get a common factor here, 7 times 1, and here we can get a factor 6 times 1. And so now we see where the 13 comes from, right? It's actually the sum 7 plus 6. And now we see what's going on. The 11 is actually the sum of 6 plus 5, and the 9 is actually the sum of 5 plus 4. And in fact, you can do the same kind of argument in general to factor difference of squares. So that's really the main reason we want to write it this way. Also, I'll just mention here, the reason we're looking for c being 1 bigger than b, if we have c 1 more than b, then we know it's going to be primitive, right? So if c is 1 bigger than b, then they're not going to have a common factor. Alright, so now we've got a lot of information because we know that these numbers on the left just keep getting bigger and bigger by 2 each time. Some of these will turn into squares, and the ones that turn into squares, well, they give us something that we want. So this is now a really good trick for getting as many primitive Pythagorean triples as we want. So let's go ahead and write down the formula that we get. Right, so again, the idea is we just have these odd numbers that are increasing. Eventually, if we continue long enough, we'll encounter a square. And so we want to be able to express the right-hand side in terms of this number. Aha, so we didn't think of doing that before. If we have this number, how do we find the 7 and the 6? Well, remember, the 7 and the 6 are consecutive in our discussion, so they're really close to each other. And the 13 is the sum of the 7 and the 6. So really, to find the 7, we want slightly more than half, and the 6 is just slightly less than half of the 13. Right, so that's always the way it's going to work. Okay, so we're looking at slightly more than half of the a squared, and we're subtracting from that a number that's just a little bit less. Slightly less than half. There, and now I can make it look a little nicer. So this is a pretty good formula. The 3 numbers in this Pythagorean triple, so let me write out the 3 numbers. We're going to have a. This will be the second number in the Pythagorean triple, and then we'll have a squared plus 1 over 2 as the third number in the Pythagorean triple. Okay, so now this brings us to the joke that I saw on Twitter. It was describing the situation where one wants to find the hypotenuse of a right-angled triangle, and the video was suggesting that instead of finding the square root of the sum of the squares of the other sides, that instead all we had to do was square this number and subtract that one. And of course, the examples that we found, these primitive triples, where the hypotenuse is 1 unit bigger than one of the other sides, of course what we have is the situation that where we square this first side, this is a little bit less than half, and when we subtract a little bit less than half, of course we get a little bit more than half. So the trick of using 3 squared and then subtracting 4 to get 5, instead of doing it the way we're supposed to, well, that trick will work for any of these particular triples. Let's see if it works for any others. Okay, and again, we're not writing a squared plus b squared equals c squared. We're going to write it this way because of the difference of squares formula, right? We really like this factorization, and we're asking the question, is it ever the case that a squared minus b is equal to c? In other words, is it ever the case that a squared is equal to c plus b? Well, if a squared is equal to c plus b, then I guess c minus b has to equal 1. And if c minus b is equal to 1, well, we've already discussed all of those cases. The only situation where this joke method actually gives the right answer would be these situations here. But before we leave this discussion, I should mention that these primitive triples that we found provide something that's actually very close to the general formula for all primitive triples. Okay, so let's just look at how this works from the perspective of the difference of squares formula. So I have here the difference of two squares. And so we find the difference of squares. Well, c minus b is just 1 in this case, and c plus b is just a squared. So we see how that works. This idea can be generalized slightly, and we'll do it this way. Instead of having a plus 1 and a minus 1 here, we can have a plus t squared and a minus t squared there. And when we do that, the left-hand side is the square of the product st. And this turns out to be the general formula for all primitive triples if you assume that s and t are relatively prime. So this little thought experiment doesn't give the whole general formula, but in a sense it gets you very, very close. To actually get this formula and drive it properly, you need some number theory. But to get this one, you really don't. We just needed the difference of squares formula.